SpaceX is a company always developing something new and exciting in rocket technology. Their Falcon 9 is the most popular reusable rocket still transferring payload to orbit to this day. But to perfect these technologies, they have done so many launches and landings. In the last 2 years alone, SpaceX has performed 39 launches, representing about 20% of roughly 200 worldwide launches. So let us discuss everything about the most reliable rocket ever made by SpaceX, the Falcon 9, in today's video of DiscoverZen. The Falcon 9 is a partially reusable, two-stage-to-orbit, medium-lift launch vehicle designed and manufactured by SpaceX in the United States. It is the world's first orbital-class reusable rocket. Reusability allows SpaceX to refly the most expensive parts of the rocket, which in turn drive down the cost of space access overall. The Falcon 9 is 70 meters, or 229.6 feet tall, with a mass of 549,000 kilograms, and a diameter of 3.7 meters, or about 12 feet. It can lift payloads of up to 22,800 kilograms, or about 50,000 pounds, to the low Earth orbit. 8,300 kilograms, or about 18,000 pounds, to geostationary transfer orbit when expended, and 5,500 kilograms, about 12,000 pounds, to the same when the first stage is recovered. It's a two-stage, LOX RP-1 powered heavy lift launch vehicle. Both stages are equipped with Merlin 1D rocket engines, 9 sea-level adapted versions on the first stage, and 1 vacuum adapted version on the second stage. Every engine uses a pyrophoric mixture of trimethyl aluminum triethylborane as an engine igniter. The first stage engines are arranged in a structural form, which SpaceX calls octaweb. Many cores include 4 landing legs attached around the base of the octaweb. To control the descent of the core through the atmosphere, SpaceX uses grid fins that deploy from the vehicle after separation. The legs deploy moments before landing. The propellant tank walls and domes are made from an aluminum-lithium alloy. SpaceX uses an all-friction stir weld tank, the highest strength and most reliable welding technique available. The second stage tank of Falcon 9 can be said to be a shorter version of the first stage tank. It uses most of the same tooling, material, and manufacturing techniques which reduce production cost. The Falcon 9 inner stage, which connects the upper and lower stage, is a carbon fiber aluminum core composite structure. Merlin engines. The SpaceX Merlin is a family of rocket engines developed by SpaceX for use on its Falcon 1, Falcon 9, and Falcon Heavy launch vehicles. Merlin engines use RP-1 and liquid oxygen as rocket propellants in a gas generator power cycle. The Merlin engine was originally designed for sea recovery and reuse. The injector at the heart of the Merlin is of the pintle type that we first saw used in the Apollo Lunar Module Landing Engine, or LMDE. Propellants are fed by a single-shaft, dual-impeller turbopump. The turbopump also provides high-pressure fluid for the hydraulic actuators, which then recycles into the low-pressure inlet. This eliminates the need for separate hydraulic drive system and means that thrust vectoring control failure by running out of hydraulic fluid just isn't possible. Although there have been many revisions of Merlin engines, the basics remain the same. The latest version of Merlin is the Merlin 1D, used in the Falcon 9 and Falcon Heavy as the first stage boosters. Here's a close look at the development of the Merlin 1D. The Merlin 1D engine was developed between 2011 and 2012, with the first flight in 2013. The design goals for the new engine included increased reliability, improved performance, and improved manufacturability. Merlin 1D was originally designed to throttle between 100% and 70% of maximal thrust. However, further refinements since 2013 now allow the engine to throttle to 40%. Your basic Merlin fuel oxidizer mixture ratio is controlled by the sizing of a propellant supply tube going to each engine, with only a small amount of the total flow trimmed out by a servo motor controlled butterfly valve to provide fine control of the mixture ratio. On November 24, 2013, Elon Musk stated that the engine was actually operating at 85% of its potential. and they anticipated to be able to increase the sea level thrust to about 730 kilonewtons and a thrust-to-weight ratio of 180. This version of the Merlin 1D was used on Falcon 9 full thrust and first flew on Flight 20. In May 2016, SpaceX announced plans to further upgrade the Merlin 1D by increasing vacuum thrust to 914 kilonewtons and sea level thrust to 845 kilonewtons. According to SpaceX, the additional thrust will increase the Falcon 9 LEO payload capability to about 22 metric tons on a fully expendable mission. SpaceX also noted that unlike the previous full-thrust iteration of the Falcon 9 vehicle, the increase in performance is solely due to upgraded engines, and no other significant changes to the vehicle were publicly planned. In May 2018, ahead of the first flight of Falcon 9 Block 5, SpaceX announced that the 850 kilonewton goal had been achieved. The Merlin 1D is now close to the sea level thrust of the retired Rocket 9 H1 RS-27 engines used on Saturn I, Saturn 1B, and Delta II. A vacuum version of the Merlin 1D engine was developed for the Falcon 9 and the Falcon Heavy second stage. As of today, the thrust of the Merlin 1D vacuum is 981 kilonewtons with a specific impulse of 348 seconds, the highest specific impulse ever for a US hydrocarbon rocket engine. The increase is due to a greater expansion ratio afforded by operating in a vacuum, which is now 165:1, using an updated nozzle extension. The engine can throttle down to 39% of its maximum thrust, or 360 kilonewtons. For engine control, SpaceX uses a triple redundant design in the Merlin engine computers. The system uses 3 computers in each processing unit, each consistently checking on the others to initiate a fault-tolerant design. 1 processing unit is part of each of the 10 Merlin engines, 9 on the first stage, 1 on the second stage, used on the Falcon 9 launch vehicle. The Falcon second stage and Falcon Heavy side booster restraint, release, and separation systems use pneumatic devices that provide a low shock release and positive force separation over a comparatively long stroke. The pneumatic system allows for acceptance and functional testing of the actual flight hardware, which is not possible with traditional explosive-based separation systems. Reusability. SpaceX intended to recover the first stages of several early Falcon flights to assist engineers in designing for future reusability. They were equipped with parachutes but failed to survive the aerodynamic stress and heating due to atmospheric re-entry following stage separation. Both stages in the early launches were covered with a layer of ablative cork and had parachutes to land them gently in the sea. But later, they removed parachutes for a reliable propulsive landing, which was an excellent decision as it's still working as intended, with hardly 1 or 2 failures after dozens of reuses. In the end, let's look at landing. The first stage is equipped with 4 landing legs made of state-of-the-art carbon fiber with an aluminum honeycomb. The 9 Merlin engines on the first stage are gradually throttled near the end of the first stage flight to limit launch vehicle acceleration as the rocket's mass decreases with the burning of fuel. These engines are also used to reorient the first stage prior to re-entry and slow the vehicle down. So this was all about the Falcon 9. Now, let's talk about the working of Starship. Well, that actually sounds like something we should talk about on a different video here on DiscoverZen.